In this video, we'll look at two ways to calculate areas by integration. Method 1. Say our area looks like this. We've got a bottom curve, y1 equals f of x, and we've got a top curve, y2 equals g of x, and let's say we know the x values that our area ranges through. Say it goes from x equal a to x equal b. Well, we can calculate the area by taking vertical slices, and this method will be valid as long as any vertical slice here ranges between the same bottom and top curve. So no matter how we choose our slice, yep, bottom and top curve are the same. Here's how the method works. dA represents the area of one of these vertical slices. Now each of these vertical slices is a rectangle, so its area is going to be height times base. The height will be y2 minus y1, and the base is going to be infinitely thin here, so we're going to use dx to represent the base, and that represents just an infinitesimal change in the x direction. Now we can say that area is the integral of dA as long as we integrate through the correct values. The fact that we've got dx in this expression tells us that we're going to be integrating with respect to x, and so it's x values that need to go onto the integral here. So we can now say area is going to be the integral from a to b of dA. Let's sub in dA. And the final thing we'll need to do here is write y2 and y1 in terms of x, because we're integrating with respect to x. So if we look back up at our region here, y2 is g of x, y1 is f of x. So we can say that area is the integral from a to b of g of x minus f of x, all multiplied by dx. So that gives us one way to calculate the area of that region. Method 2. I'm going to draw that exact same area again, and this time we're going to describe it differently. So let's think of it as a left curve and a right curve. The left curve we might call x1, and let's say that's some function of y. So x1 equals u of y. And then for our right curve, let's say x2 equals some other function of y. So x2 equals v of y. And in this situation here, we would know the y values that our area ranges through. So let's say our area starts at the y value, y equals c, and goes up to the y value, y equals d. To calculate the area, we're going to take horizontal slices this time. And this method will be valid as long as any horizontal slice is bounded by the same left curve and right curve. So no matter how we choose our slice here, we've always got x1 on the left, x2 on the right, so this method will work well. dA will represent the area of one of these horizontal slices, and since these slices are rectangles, their area is going to be base times height. So the base will be x2 minus x1, and the height is going to be just a tiny change in the y direction, which we'll represent as dy. Now that dy there tells us that our integration is going to be happening with respect to y. So we can write a is equal to the integral of dA provided that we put y values on this integral here. So formally a would be the integral from c to d of dA. Now let's sub in our expression for dA. And the final thing we need to do in order to be able to integrate is to get x2 and x1 written in terms of y. So for that, we'll go back up to our region here. x1 has equation u of y, and x2 is equal to v of y. So if we sub in here, then we can say that area is the integral from c to d of, it's going to be v of y minus u of y times dy. So since we've talked about the same area in two different ways, both methods here will give us the same answer. And depending on the specific problem, one method might be much easier than the other. So it's important to be familiar with both methods.